Hi guys, welcome to our next video on this Python series. We've gone through quite a lot already, so we've learned the basics of data, we've learned how to use Numpy, so we're importing stuff, and then I went through a bit of not a tangent, quite a really important lecture in effectively what is Python, how do we do things with objects, how do we do things with their parameters, their attributes and their methods. What we're going to move on to now is plotting. Now, plotting is superbly important. So we're doing plotting. So as engineering students, you guys will need to make plots all the time. So we're learning how to make good plots. Okay, so how to make plots that are clear, that have got good axes labels. And then we're going to do some really important things. So we're learning how to import data in order to plot it. So we've got data in another file, we're going to import it. So this first one that we're looking at is importing data from CSV. And CSV stands for comma separated values. Okay, so we're going to make some plots. What we're going to do is plot things. We're then going to fit lines of different sorts. We're going to look at some polynomial fitting. Polynomial fitting is, common sense, fitting a polynomial to it. And then we're going to look at fitting some more advanced functions. And we're also going to look at how to export plots and diagrams. And this is really useful. So typical undergraduates will make a plot using Python or using MATLAB and then just take a screenshot of it to put it into a report. And that, quite frankly, looks shit. Okay, so we don't want to do that. We want to have a plot that looks nice, crisp, clear, infinitely zoomable. So we want to make sure that if it's in a non-vector format, we take it at suitable resolution, and ideally we want to take data in a vector format. So there's some data files that I want you guys to download, and they should be available either in the YouTube link or on the Slack space. There's two data files. We've got two here. Cessna drag polar, which is some data for the lift and drag of the Cessna 172, and resistor 1, which is some data about a resistor from the third year course actually. So just to show you how things should work, those data should live in a folder called data, and that should be within the same directory of the Python notebook that we're about to make. So I'm going to make a new Python notebook, and this is, I think, is this lecture 4? No, this is lecture 5. So let's call this lecture 5. Okay, so we're starting lecture 5. We are going through plotting in Python. Now the package that we're going to use in this first instance is matplotlib. Matplotlib is probably the most basic but very powerful plotting routine available within Python. Others include Plotly. Plotly I use for my website because it enables you to create HTML plots that are really powerful. But for the basics of what you're going to do in your undergraduate studies, Plotly will do everything that you need. So the very first step that we're going to do is just to import it. So we'll do imports, and the syntax that we use to import it, we do matplotlib.pyplots. So we're using the part of matplotlib called pyplots, and we're going to import it as PLT. Now that's sort of standard nomenclature across the interwebs for how matplotlib.pyplot should be imported. So in order to plot something, we need some data. So let's use Numpy to plot a sine wave. So we're going to make some sine data. I'm going to say import Numpy as NP, as we always know, as we always do. And then I'm going to make my x data is just going to be a linearly spaced vector. I tell you what, let's say we're going to make a certain number of sine waves. I'm going to make 6 sine waves. So I'm going to say x is equal to a linspace from 0 to 2 times pi. So it should be np.pi times n. And I'm going to put 10,000 values between them. Just a value that I've, just a value that I've chosen, 10e5. Okay, and then this is my x vector. So my y vector is going to be equal to the sine of those. So if I run this, it takes a moment to load up, and then I've got those data. I can look at them. I can do print x, print y. Bearing in mind I've got 10,000 of them, it doesn't really mean very much to B. So what we're going to do is we're going to plot these data. So we've already got this imported. So let's do our very first plots. So the way that we make plots is we very first make a figure. We're going to say our figure is equal to plt.figure. And that's a method, so we supply it with the square brackets. If I run that, I've just got this figure available. Okay, so it's there. I'm then going to put a set of axes on top of it. So I'm going to say x, and the axes that we're going to plot to is equal to plt dot add subplots. And I'm not going to supply any arguments yet. Oh, so I need to do that to the figure, not to the PLT. So I need to the figure, I'm going to add a subplot. So I've got a nice empty graph now. And then I'm going to use a method of axes. I'm going to use the plot that belongs to axes to do a plot of x and y. And I'm going to say ax.plots, x, y, and I'm going to call it, so we say label is equal to sine x. Okay, so I've given it a label, but it hasn't done anything with it yet. So I've got this graph, which is what we wanted, which was 6 sine waves. Let's make a y2 here as well. Let's say y2 is equal to sine of 3x. And then I'm going to plot this as well. So I'm going to call this sine of, this very first one is sine x. This next one is sine of 3x. Oh, I haven't plotted y2, that's why. So before I just had y, let's make this y2. I've got my 2 graphs being plotted. Now I can't distinguish between them. I've given them labels, but I haven't told them to do anything with it. So I'm going to put a legend on there. I'm going to put, let me just check, let's try fig.legend. It might be act.legend. Nope, I've got a legend here now. Okay. So I've got these here. Now a good graph should have an X label and a Y label. So I'm going to set those on the axes. I'm going to set ax.set title is equal to 2 trig plots, because we can. X label, X, Y label equals to Y. There we go. So we've got this graph here. What's useful to do, we see here actually this part here has just been printed out because it was the very last thing that was in my cell. If I put a semicolon here, it will stop that from exporting. And we've got our plots here. Let me just delete this cell. So what else can we do to this? Let's play around. It would be nice to have this going from 0 to the full value up here. Before we do that, I'm going to show you a little trick that's helpful. If we tell matplotlib that we're working in a Jupyter notebook, then we can get some more interactivity to our plots. So let's try first off, let's see if we can make this interactive. I'll do a %, and I say matplotlib interactive. I think this works. No, it doesn't like it. Okay, let's try notebook, matplotlib notebook. There we go. Okay, this has given me an interactive plot that I can choose to go home. I can zoom in on, which is useful. I can pan around it, and I can go home to my original view. Just we're going to make this plot a little bit better. We're going to get the grid to go to the maximum and the minimum, which is where we want to go to. So let me just think about how to do that. I'm going to go to So let's narrate this a little bit. So we're going to say add a legend. We're now going to set the limits. And the way that I'm choosing to do this, there's many ways you can set the axes limits. I'm going to say ax.set xlim. And I want the left to be equal to 0. And I want the right to be equal to the maximum value that this can have here. So we'll just make that equal to x max. There we go. So we've now got our graph taking up the whole of the horizontal axis on our plot, which is really useful. It would be nice if we could have a grid on there as well, to put some grid lines in. So we do ax.grid. There we go. So you can move your mouse around and it shows you the x and the y coordinates on this plot as well. So we've got a nice simple plot here. This is how we can do this. Let's export this as well. So we've got a plot here. We can plot anything we want if it's some sort of vector. Okay, these can be lists or they can be Numpy arrays, which is what they are here. Let's export this. Like I say, most students will have a tendency to take a screenshot of a plot like this. And once they've got that screenshot, this is then what they choose to put into a report, for example. So let's just see why maybe we shouldn't do that. Can we zoom in on here? Let's see if I can open this in preview. Yeah, I'll open this in preview. Just say I've got this as my plots. Let's zoom in. We can see here that I've got blurring occurring, and this would be really bad to have in a plot. So what we can do instead is we'll export this in different formats. It's really easy to export graphs, thankfully, from matplotlib format. It's just a case of saving the figure. So, let me not have my screen show up like that. The clapping is so I can look in the time and see when I need to edit the video. So what we can do, we can export the figure nice and easily, and it's just using the syntax save fig. So we save this whole figure. I'll do 3 different versions. I'll do fig.savefig. I like to save figures as PDFs. So I'm going to call it exported figure.pdf. Do it 3 times. PDF, PNG, and SVG. Okay, so it will have saved all of those versions. Now let me just show you those figures. So the PDF, let's delete that. So the PDF is very useful because if I zoom in, we see no blurring occurring here. PDF is a vector format. PNG is not a vector format, but it can have high resolution if you choose to. So we still get some blurring occurring in the PNG. SVGs are very useful. It's called scalable vector graphic file. I recommend you get a piece of software called Inkscape, which helps you edit things. It's a very, very useful SVG editor. But what this would enable you to do is once you've got your SVG, you can then open it in Inkscape. And let's show you this here. If you get Inkscape working, you then got a graph you can then manipulate. So I could say, I've got this here. I want to degroup different parts of it. I'd like to move the legend, and you can then change what these axes say if you wanted to. So I could ungroup everything. This is then, these aren't text unfortunately, but you can play around with them. I can delete parts, I can delete the whole plot if I wish to, or I can ungroup them and say get rid of these lines. These are much better ways of exporting graphs than just taking pictures of them. So they're really useful. And guys, a lot of what I'm trying to tell you in this course as well is lectures that maybe are a bit over your head with some of the stuff, but you'll come back to this in a couple of years, maybe when you need to do some of your reports for a 3rd year course and think, Professor Smith told me how to export a plot properly. I'm going to remember to do that next time. So that first bit was making a simple plot and then exporting it in a clean vector graphics format. So let's try doing something more interesting now. We're going to import some data from a CSV file, and we're going to fit a line through it. So let's have a look here. In my data folder, I've got resistor1.csv. Let's open this up as a text file. It wants to open it with Excel, but I'm going to choose to open it as a text file. So I've got 2 columns of data. I've got voltage and I've got current. So it's looking at a resistor, looking at the voltage across it and the current through it. So if I plot those data with voltage on the vertical axis and current on the horizontal, the gradient of that line should be the resistance of this resistor. So let's try that out. So what we want to do is we want to import that data. So I'm going to tell it where to find that file. So remember, it lives in that folder called data, which is in the same level as where this notebook lives. So I'm going to say, tell it where to find the data. So I'll say my file name is equal to a string, which is data, which is the folder / resistor_1.csv. So that's my file name of that file. Hasn't done anything smart yet. I need to actually make it read it. So we're going to import it using a part of Numpy. We're going to use the method gen from text, which means generate from text. And we're going to call this our data is equal to numpy.gen from text. Oh, didn't want to make a new tab. Gen from text, and I need to tell it the file name. I'm going to tell them that it's delimited with commas because this is a comma separated value. So I'll say my delimiter is equal to comma. And I'm going to tell it that it's got 1 header line. And that's because if we remember back to this text file, the header doesn't contain any data. So if we try and import that, it's going to cause a bit of confusion. So we'll say skip underscore header equals 1. And I'm going to do print data. Oh, it's because this is called gen from txt, not gen from text. Why is that? MP gen from text. Let's see what's happening here. Type error. Gen from text got an unexpected keyword argument delimiter. Okay, that is because I've written delimiter, not delimiter. Delimiter is something in a text file that separates values, spelt with an I. A delimiter would be a measurement device that measures where delicatessens are. Okay, not what I meant in this case. So with this now, and those mistakes ironed out, this has now printed my data as a NumPy array. And we can confirm that it's a NumPy array by doing type of my data, and it will tell me what the data is. Okay, it's class of ND array. And remember, I could have also written type data.type. Oh no, it doesn't work. Let's see how I can find that out actually. Let's do help data. It tells me it's an ND array object. Parameter could tell me the data type there. Okay, I do actually have to write. There is no attribute that tells me that the type in the same sense that I could have written print type data. Again, some of this I'm just showing you that I know how to do lots of things in Python, but I'm always learning as I'm going along. Okay, so I'm always learning different ways of doing things, and I'm happy to sort of make mistakes and try new things as we're going through this. So now we've got these 2 bits of data. Let's rename the 2 vectors. So it was the voltage was the first one, the resistance was the second. So let's say we've got voltage is equal to data. I want every row first column, and then the current is equal to the data, every row second column. So now we've got these 2 sets of data. Let's try and plot them, and I'm going to make a mistake on purpose. Hopefully we'll see what happens. So we'll do ax.plots, current, voltage, and I want red crosses. Okay, so because x is this axis up here, I've just, I haven't overwritten, I've just included it in this trig plot, which is not what I wanted. So what I need to do in this case was make a new figure. So fig is equal to plt.figure. Make a new axis. Axis is equal to fig.add subplot. And there we go. I've got my data being shown now. I'm just going to put on here as well. Let's call this this is data. Experimental data. We're going to put a grid on here as well. Okay, so we've got that here. I can also see that this doesn't go to 0 on either side. So let's make both the x and the y go to 0. Let's say x.set xlim left equal to 0. And I don't need to tell it what to make the right equal to, because I don't care where the right is. And I'm going to, with the y limit, or the vertical limit, I'm going to set the bottom equal to 0. I don't like that. Let's move these two below the plot. I think that's what happened there. There we go. Okay. Sometimes if you try and mess around with the axes before you change a plot, you can confuse things a little, or before you plot any data. So let's just label these as we did before. Let's say x.set title. Here we go. So we've got our plot now. Now what I want to do, so we don't need to really get into the analog electronics of how this works, but you guys might be comfortable with Ohm's law, which is the voltage or the current through a resistor is proportional to the voltage across it, with the constant of proportionality being the resistance. So if we fit a straight line through here, then the gradient of that straight line should be equal to the resistance. So what we're going to do is we're going to fit a line of best fit. We're going to use something called Polyfit from Numpy. Now Polyfit helps us look at polynomials. So polynomials are straight lines, quadratics, cubics, quartics, quintics, and I can't think of any more what the terms are, but they are effectively relationships between two, say y is equal to x, or it could be y is equal to a constant plus x, y is equal to x squared times something plus x times something plus a constant as well. Okay, I probably don't need to tell you what polynomials are, but what we can do is with these data is we can fit a polynomial through it. So we're going to fit a polynomial of order 1, which is a nice straight line. So we're going to fit a polynomial. So we're going to get an output, which is a polyfit is equal to np.polyfit. So it's a method of Numpy. And all we need to tell it is the current, the voltage, and the order of the polynomial. So I'm going to put it of order 1. And let's have a look at what we get out of here. What we get out is 2 coefficients. Okay, so this is our this is our gradient of the line, and then this is the offset, the intercept. Okay, so we should expect this number down here to be about 0.18 where it hits the graph, and then it's going to go off up at this angle up here. So I can use these 2 values to calculate the x and the y of my graph. So I'm going to want a line now that goes from x is 0 all the way to the maximum value of x up here, and I'm going to work out the corresponding y values using this polynomial line. So I'm going to say line x, which is the x component of the line, is equal to just two values is all I need. The first one is going to be, let's make it a Numpy array. First value is 0, and the next value is going to be the maximum value of the currents. And then the corresponding y is equal to Polyfit 0, which is the first bit of polynomial fit, multiplied by line x, so that's the gradient, plus Polyfit 1. And then I want to plot this line on here, just on the same graph. So I'm going to do x.plot, line x, line y, blue line. I'm going to make it a blue line, and I'm going to call it linear fit. And let's put a legend on at the bottom. So we'll say x.legend. There we go. So we've now got data and we've got a linear fit through there. Let's tart this up even more. Let's say, rather than just printing linear fit, let's put our polynomial through here. So I'm going to say that the linear fit through here, the bit that we care about for this particular graph would be the gradient. So I'm just going to say my resistance is equal to pfit naught. I'm going to just put $/omega. This gives me latex formatting, which you guys don't need to care about too much. But what it enables us to do is use, why isn't that working? Pfit, I've used the wrong thing. I should have written Polyfit. This bit here enables me to get a nice omega here. Okay, so my resistance of this resistor, 325 milliohms. So that's really useful. I'm going to introduce one more useful bit of number formatting that will help you guys, and I'm just going to import it up here. I'm going to say from SI, let's say from SI underscore prefix imports SI formats. And then what I can do is, okay, let's run this first. It's going to produce that first plot. I don't know why I've imported that up there, but I've got it available now. I'm going to write SI format here, and I want it to 2 degrees of precision, and then I get rid of the number formatting. There we go. So SI format gives you the correct SI prefixes for things. It's a very useful tool to be able to import. 325 milliohms. Very useful. In fact, let's just get rid of the decimal places. Let's say none. There we go. 326 milliohms. Very useful. So what we've done there is we've taken data, we've imported it, and we've then fitted a line of best fit through it using Polyfit. So let's do that again, but let's try it using Polyfit with a slightly higher order now. So let me do this with a quadratic. Just to show you how powerful Polyfit is in terms of fitting data. Let's make a new vector. X is equal to mp.linspace -10 to 10, and let's give 25 data points between there. I'm going to make a new function that's going to help us produce these graphs easily. So I'm going to say define something called the quadratic function. X, A, B, C. I'm going to say that QF is equal to A x squared plus B times X plus C. And then I'm going to add some noise to this data. So this is a quadratic function with some noise. So I'm going to do mp.random. And I need to add a vector the same size as my input x vector. And let's make this something that's 10 times larger, because the np.random.random gives you values between 0 and 1. So I'm now adding a random decimal number between 0 and 10. And I want it to return that QF. So let's just see what that looks like. Let's say that my y now needs to be equal to quadratic function, and I want to put my x vector in there, and I need to now pick some numbers for my different parts. So let's say 2, 1/2 and 0.25. I've just chosen those numbers randomly. Now what I'm expecting to see is 25 values of x and y. Oh, I didn't put a plus sign there, that's why. Okay, 25 values of x, 25 values of y I've got here. So what I can do now is I'm going to plot this out. Let's do fig is equal to plt.figure. X is equal to fig.subplot. And let's do x.plot x, y. Oh, syntax is slightly wrong there, isn't it? Because I should have put up here, add subplots. Okay, so these are my sort of quadratic data with a bit of noise in here. If I didn't include the noise, if I multiply the noise by 0, or by 0 rather than a closed bracket, I should put, I get a perfect quadratic. But I'm leaving the noise in just to show you that we can fit curves to noisy data. So that's my original graph. Now let's try and use Polyfit to fit a polynomial curve back through those data. Okay, so I'm going to say that my Polyfit is equal to np Polyfit x, y, and I want it to be of order 2, second order polynomial now. I'm then going to make a vector of x that's got many more points than were originally in here, and I'm going to put data through there. So I'm going to say x vector is equal to np.linspace. So I'm going from the smallest to the biggest value of x, and let's choose 1,000 points. Okay, so we've got 40 times as many points as were originally in this vector. So my y vector, so previously what we did when we had this polynomial, we used the definition of how the polynomial works to get the different values out. Instead of doing that, I can use np.polyval. So I can use polyval, and all I need to then give this is the polynomial object, polyfit here, and the values at which I need to interpolate it. Sorry, not interpolate it, the values at which I need to evaluate it. So that's my x vector here. And I'm then going to do x.plots x vector, y vector. I'm going to make it a red line, and for good measure I'm going to print out the polynomial. So let's say print So remember, we've enforced these data to have a quadratic of the form 2x squared plus half x plus a quarter. And we're now trying to fit some data back through it. And hopefully what it will print at the end is the fit that goes through it should be very close to those numbers. There we go. So that's our fitted polynomial. Nearly 2, nearly a half. Why is that giving me 5 there? Oh, okay. It's because everything's got an offset because of the... I've included the noise in here as well. So everything's been slightly shifted because of that offset noise there. Okay. So if I didn't have the noise in here, it would get the numbers exactly correct here. But it's because of that noise. Yeah. Okay. Interestingly, if I subtracted half the mean value of the noise, or the mean value, I think it would get me much closer down here. Yeah. We're not going to worry too much about that because we're getting into sort of more complex fitting, but I just want to show you what that line of best fit looks like through here. Okay, so we've done 35 minutes of fitting. Let's do one last good fit, and this is going to be quite a lot more complicated, but I want you guys to be mind blown with some of this and a little bit saturated towards the end. Okay, so we're now going to fit some drag data to some Cessna data. Let's just think about what this looks like. Now we're going to look at something called the drag polar of an aircraft. So the Cessna 172 is the aircraft we're looking at. And I've got some data for the drag polar. Now the drag polar of an aircraft, we normally plot it as CL versus CD, but I'm actually going to plot it as CD, CL here. Okay, and it's normally data that looks like that. Okay, so we see some data that looks like this, and we're going to try and fit some numbers to it. So what I have for the Cessna 172 are these data points, okay, and that's what exists in that CSV file. So we're going to import those, and we're going to mess around with them, and we're going to fit something more complicated to them than just the original polynomial. So those data files exist in here. Data, it's Cessna drag polar CSV. If I open it, we can see it's CL and CD, some very big numbers in here, okay? And by big numbers, I mean long numbers. They're not that big. None of them is going to be larger than 2. So, let me check I'm still recording. Oh, probably don't want the drag polar up on the screen, so let's get rid of that. So the file name is equal to data Cessna drag polar.csv, and I'm going to use the exact same line that I did up here to import the data. Let's print the data. Okay, so we've got CL and we've got CD here, so lift coefficient and drag coefficient. And I can just rename those data. CL is equal to data, every row, first column. CD is equal to every row, second column. So I've got all of those now. Let's make a new figure and plot it. So okay, so this is now my flight test data for the Cessna 172. Let's just put some labels on here. Let's do x.set x label equals. Now I'm going to show you a little bit of LaTeX. So it's $ C and subscript L is C_L, and then CD. There we go, CL versus CD here, or CD versus CL rather. So what happens if we try and now fit a polynomial through these? Well, let's give it a go. So we'll try and fit a quadratic through here. We can see that it's got some sort of quadratic curve to it. So I'm going to say try and fit a quadratic. So pfit is equal to mp.polyfit. And then it needs to be CL, CD, oh no, it's got to be of order 2. And as before, I'm going to say CL vector, which is the vector of values that I want to try and evaluate, is equal to np.linspace cl.min, cl.max. And I'm going to put 1,000 points in between. So my CD vector is equal to np.polyval, and then it's going to be pfit CL vector. So let's plot those on there. Let's say ax.plot. Okay. So we've now, oh, I haven't called it something. I need to say label. There we go. So it's not a very good fit, really, is it? The quadratic is not a good fit to these data, and I knew that was going to happen. So this is the issue with just using Polyfit, because we don't always want a perfect polynomial to be fitted. The reason for that is because we actually have a very good model for the way that this gets fitted, and the model that we use is CD is equal to CD naught plus K CL minus CL naught squared. So you don't need to remember this, I'm just showing you this is our model. So let's highlight the things that we've got. So this here is our x ordinate. This one here is our y ordinate. Everything else are just some constants that we're going to fit to it. So we're going to define this as the fit that we want to have to our data, and then we're going to use another smart bit of Python to tell us what these numbers must be, okay, in order to make this fit work. So remember, we've already got these. This is what we have. And then these bits is what we'd like. And if you're astute and you're looking at this, you'll see, well, this is still a quadratic. It's just it's a quadratic rather than being in CL squared. It's in CL minus CL naught squared. So it's quadratic here in these terms. And we've also got no linear term. There's no CL multiplied by anything. We've only got CL minus CL naught squared in there. So let's do this. Let's put that model in and let's see if we can work out how to fit data using it. I realise as I'm going through this is a little bit complicated for a first year course, but I want you guys to have this and saved, because no one's going to show you how to do this at a later date. So when you come back to it, you guys will know how to do it. Okay, so we're going to use something called Curvefit from Scipy. Now we're going to use Curvefit, and we need to tell it what our drag model is going to look like. So first, we define the drag model for our fit. So we make a function. We say define drag model, and drag model is going to be a function of CL, which is the lift which we input, and then those three constants, CL naught, let's make it CD naught, K, and CL naught. And those are just going to be some numbers that we get out. So that's our drag model we're looking at. And then I'm going to say that my CD is equal to CD naught plus K multiplied by CL minus CL naught all squared. And I want to return CD. So if I run this, it hasn't done anything smart. I've just defined this function. It's a function that we're going to use, and we're going to try and work out what the values from it are. And the way that we do that is we import the Curvefit module from scipy.optimize, from the optimization part of Scipy. So we're saying from Scipy optimize import curve_fit. Okay, and then all we need to do to get those coefficients out, we'll say that our coefs is equal to curve underscore fit. Now we're going to tell it what we're trying to work with. So we say drag model, and then we're going to fit it to CL and CD, which is the CL and CD values that we care about. And then for reasons that I'll go into a little bit later, we can just tell it to pick the first object because it actually outputs several things here. Well, in fact, let's have a look. So let's do let's import the module first, and I then want to look help curve fit. What I'm trying to see here is the outputs. So it returns two things. In fact, so I won't be lazy. What I will do, because it's supposed to be returning two things and I've only given it one output here, I can tell it to expect a second output and then do nothing with it by putting this underscore there. So in fact, let's just put these directly into an output, which is going to be CD naught, K, and CL naught. So those are our coefficients. So if I run this, it doesn't like that. Okay, so I'm going to cancel that. Let's call this coefs. Okay, let's not do that. Let's do what I was... that's why, sorry, it's because I put this 0 at the back here. I don't need that back. Okay, it's me trying to explain things in once. So what I can do is I know this coefs is going to be... It's going to have worked out what these values are. CD0, K, and CL. So I can put this in here. And now it's saved those values out for me. So let's do print CD0, print K, print CL naught. I know from experience that those are all pretty reasonable values. CL naught's a bit high, and I have a feeling about why. But let's try and use those to plot those data. So I can then use this drag model that I've made to go with those coefficients that I've just discovered, and I can plot those data. So I can say we'll say CD plots is equal to, we're going to use this CL vector and we're going to supply it into here. So that's equal to drag model, CL vector, CD naught, K, and CL naught. And then I'm just going to, oh no, not that. Okay, so if I now plot this, okay, so my drag model hasn't done much better in this case in this quadratic fit. So what I want to do is see, okay, well, I'm going to look at values where I don't have this really high bit up here. So I'm going to choose CL that is less than 1.5, for example. So I'm going to tell this up here where I use my drag model to only use, I'm using logical indexing or Boolean indexing, CL is less than 1.5. And I also want to use the corresponding CD values where that's less than 1.5. There we go. Okay. So let's put that there as well. So that's a much better fit. Okay, I've got the data down here. Now if I want to zoom in, what is really important, and you'll learn the importance of this later on in your studies, is that you get the bottom of this curve correctly. Because this curve goes down lower, the quadratic fit doesn't do a very good job of fitting those data. Let's see if I even constrain the quadratic fit to go where was it? Fit in the quadratic. If I do the same constraint here, let's just see if that does any better. So what I'm telling it to do is fit a quadratic, but only look at the CL values that are left of this point. So it'd ignore these higher ones. Yeah, they both do about the same actually. They are both doing the same job there really, because this is obviously just the same format. But this drag model here, which is this one, this drag model here, these parameters are something that you'll find incredibly useful when it comes to getting into aircraft flight mechanics, because this is a model that we actually use. CD is equal to CD naught plus K CL minus CL naught squared. Okay, because using the quadratic, what we found was CD was equal to ACL squared plus BCL plus C, and you could probably work out that these two are the same, but A and B would be some other relationship between K and CL naught, and that's not in a format that we want to use. So let's zoom out from here. I have given you a lot today. Okay, we've gone through a lot in 50 minutes, and I'm not expecting you guys to have really learned everything. I want you to have an appreciation of the different sorts of plotting we can do. At the absolute minimum, what I want you guys to have is to know how to import matplotlib and then to make a plot of two different vectors. And then once you've got that, you can label the axes and do things with it. I'm actually going to share the notebook and the data for this one at the end of the week so you guys can go through, but I'll share the data immediately, and I want you guys to be able to go through and just pick up what I've done, because my purpose with these are that you don't necessarily have all of the lessons remembered now, but you've got some notebooks that when you want to do plots later on in your academic careers, you've got these notebooks to think, oh man, I've done something like this in the past. Professor Smith showed me this, and you've got that, it's there for you, and you'll be able to use it in the future. So thank you very much for your time today, guys. I will see you next week. Take care.